Welcome to Analytic Resilience. In the last session, we discussed the benefits of using a three-dimensional risk map instead of the traditional heat map. Today, we will talk about the importance of using the correct formula to calculate the probability in risk assessment. We will see how probabilities are applied many times carelessly, forgetting that every formula has its restrictions. Knowing the phenomenon and building an accurate model are critical to have consistent results. For instance, it is not equally useful to apply Monte Carlo method to calculate the probability of raining in a certain interval in a certain area than the probability of hitting the blank in a darts game. One of the parameters on risk assessment is probability, which is independent from the risk assessment tool. Taking into account that impact and probability share the same problems when working with a discrete risk map, for the sake of a better understanding, we will use the traditional risk map to prove how a light probability calculation leads to wrong risk results. Okay, it's time to answer a question you possibly have. Why going so rigorous when the things could be done easily? The reality is that risk level is usually proportional to the attention and the money required to design and implement the new controls. Many years ago, I was helping a process leader to do his 2 year risk assessment, and I asked him how many times the process got interrupted in that period. He answered 5 times. As the usual probability formula is the number of events over the number of years, this gives a probability of 250%, which is not a probability, to which the risk department suggested to refine the assessment with a second question: which have been the worst events? Unfortunately, simplistic solutions tend to cost a lot. We shouldn't add complexity to what is simple, but cutting edges to avoid analysis just because we have no need to complicate things is something else. Even more when the efforts and money follows the risk assessment results. When we assert that a process probability of disruption is 50%, only because it has had one disruption in 2 years, we are assuming that there have been only two chances for that process to fail in those 2 years. By the way, the Monte Carlo method is widely used in a lot of processes, sometimes assuming that a large amount of data outweighs the need for a deeper understanding of the phenomena whose behavior we want to infer. In the last session, we analyzed the problem of sudden risk level jumps due to a discrete risk map, and we discussed the importance of relying on a mathematical definition, which is the surface in a 3D space based on a formula whose result depends on two independent variables, probability and impact. We saw the importance of having a three-dimensional risk map instead of a traditional heat map, especially when the impact varies along the impact axis. The typical impact scale is discrete, and this makes that an impact above 1, say 1.00001, is essentially the same as an impact beneath 2, for example, 1.99999. In a discrete risk map, the probability has the same behavior. There are other two additional important problems that have a direct impact on risk assessment and that are usually considered not a subject of risk management when they really are. I'm talking about the maturity of an evolving system and the time of disruption. These problems will be covered in a future session, but let's focus on the problem of a wrong probability formula. If every square in the heat map has a 20% span over the probability axis, this is 5 squares add up 100% probability. The error margin, or the maximum error, is about 20%. This is a risk in the yellow square goes from 0.20001 to 0.4. This produces an error margin of about 20%. While here, moving from the yellow square to the next green one produces an error margin of about 0%. Squared probabilities do exist, but we have to know where they apply to avoid such results in our risk analysis. Now, considering the probability formula, if the formula does not fit our case, for example, when Monte Carlo is used to calculate the probability of disruption without considering the events rate curve, we will have more serious consequences like this. A discrete probability scale, for its own nature, will adapt its own error margin, whichever be the formula. The inaccuracy we reviewed before in the yellow square will be present in all squares, including this orange square. Again, an error passing from the orange square to the red square will be the least significant error compared with that of moving into the orange square itself. As a result, we have an error that, if corrected, means turning a critical into a significant risk, which in turn may represent the difference between hundreds of thousands and a few dollars. On the contrary, if we underestimate a risk due to a wrong probability formula, we may be exposing the organization to an important risk, ignoring a possible crisis. In 2019, I derived a formula known as the VRPD theorem to calculate the probability of variable rate events. It is particularly useful for organizational processes or IT systems. The orange curve is a model of a process or system rate failure. With the process rate curve, it is always possible to calculate the probability of disruption applying the VRPD theorem. And as it happens with the 3D risk map, once the model is built for the given process or system, the calculation is just a matter of introducing the useful parameters. In this case, the time interval where the probability of disruption is to be calculated. Thank you very much for joining and see you in the next video.